Welcome to the first part of our Professional's Guide to Exploratory Data Analysis in Geochemistry. Exploratory Data Analysis, or EDA, is the critical, non-negotiable first step in any rigorous geochemical investigation. Geological data is inherently complex. It's often inconsistent, incomplete, and collected from spatially irregular locations. This challenging nature makes a systematic EDA methodology essential for uncovering meaningful patterns, quantifying uncertainty, and making sound geological and economic decisions. A failure to properly explore your data at the very beginning can lead to flawed interpretations and costly errors in resource estimation or environmental assessment. This guide is grounded in the discipline of geostatistics, which serves as the bridge connecting geological science with robust statistical analysis. Its purpose is to give you the tools to interpret complex datasets, predict the distribution of ore bodies, and minimize the uncertainty inherent in these studies. To begin this process, we must first establish a firm grasp of the foundational statistical concepts that form the language of our data. The bedrock of any valid statistical analysis is the correct identification and classification of the data itself. Different types of data require different analytical and visualization techniques. Understanding these distinctions from the very beginning is fundamental to ensuring the integrity of your entire workflow. So let's detail the fundamental classifications of data and the sampling principles required to ensure the data we collect accurately represents the geological reality we aim to understand. Geochemical data can be broadly divided into two primary categories: qualitative data, which describes characteristics, and quantitative data, which represents numerical measurements. First, let's look at qualitative or categorical data. This includes nominal and ordinal data. Nominal data represents categories that cannot be logically ranked or ordered. Think of rock types like granite or basalt, or even gender and nationality. Ordinal data, on the other hand, represents categories that have a meaningful order or rank, but the differences between those ranks are not quantifiable. Examples here would be mineralization grades like high, medium, or low, or different educational levels. Next, we have quantitative, or numerical, data. This is further divided into discrete and continuous data. Discrete data can only take specific, distinct values, which are often integers. For instance, the number of students in a class or the number of ore veins identified in a mine. Continuous data, however, can take any value within a given range. Think of element concentrations in parts per million, temperature in degrees Celsius, or weight in kilograms. Now that we understand data types, let's discuss a crucial concept: population versus sample. In statistics, the population refers to the entire group of items we are interested in studying. The sample is a smaller, manageable subset selected from that population. For example, the population could be all of the rocks contained within a specific mine. The sample would then be a collection of, say, 30 rock samples taken from that mine for chemical analysis. We rely on samples because analyzing an entire population is often prohibitively expensive, time-consuming, or just logistically impossible. The validity of any conclusions we draw about the population depends entirely on the quality of our sample. Therefore, a sample must meet three critical requirements. First, it must be representative, meaning it accurately reflects the characteristics of the entire population. Second, it must be scientifically chosen, collected using a deliberate, methodical approach. And third, it must be unbiased, meaning the selection process doesn't favor certain parts of the population over others. The method used to collect a sample is a crucial determinant of its quality. Let's review some common techniques. Simple random sampling is where every member of the population has an equal chance of being selected. A geological example would be selecting random grid points within a survey area to collect soil samples. This method is simple and free from bias, but it may not be fully representative if the population is highly varied. Next is stratified sampling. Here, the population is divided into distinct subgroups, or strata, and a random sample is taken from each subgroup. For example, dividing a study area by rock type granite, basalt, sedimentary layers, and taking representative samples from each rock unit. This ensures better representation of a diverse population but requires prior knowledge of the population's structure. Then there's systematic sampling, where samples are taken at fixed, regular intervals. A classic geological example is collecting a rock chip sample every 10 meters along a drill core. This method is highly efficient but carries a significant geological risk. If the sampling interval aligns with a cyclical geological feature, like sedimentary bedding or regularly spaced veins, the resulting dataset will be severely biased. Cluster sampling involves dividing the population into clusters and then randomly selecting entire clusters for sampling. For instance, dividing a large exploration area into sectors or clusters and choosing 3 entire sectors to sample comprehensively. This is economical for large, dispersed populations but may require a larger sample size to achieve the same level of accuracy as other methods. We also have convenience sampling, where samples are chosen based on ease of access, like collecting rock samples only from areas close to a road. While fast and inexpensive, this method is not scientifically recommended. It's highly prone to bias and is unlikely to be representative of the whole area. Finally, there's purposive sampling. Here, the researcher uses their expert judgment to select samples most relevant to the study's objective. Imagine a geologist with extensive experience intentionally selecting rocks that show visual signs of mineralization for early-stage exploration. While subjective and unsuitable for resource estimation, this method is invaluable in early-stage reconnaissance. An experienced geologist's eye can rapidly identify high-potential targets, making it a pragmatic tool for focusing exploration efforts. With a properly classified and representative dataset in hand, the first practical step in our workflow is to prepare and clean the data to ensure its analytical integrity. Data cleaning is a foundational phase that ensures the reliability and accuracy of all subsequent analyses. Raw data is rarely perfect. It can contain errors from data entry, equipment malfunction, or inconsistent recording practices. This process involves systematically identifying and correcting these errors, inconsistencies, and missing values to create a robust dataset ready for true geological exploration. Let's walk through a 7-step methodology for data cleaning. Step 1 is handling missing values. Missing data points are common and must be addressed carefully. If the number of rows with missing values is very small, they can simply be removed. For larger instances, missing values can be replaced or imputed using statistical estimates. Common techniques include using the mean for normally distributed numerical data, the median for skewed numerical data, or the mode, which is the most frequent value, for categorical data. Step 2 is managing outliers. Outliers are data points that are abnormally distant from other values. They can be legitimate extreme values, like a high-grade ore sample, or they can be errors. Outliers can be identified visually using a box plot or statistically using methods like the interquartile range or z-score. Depending on the cause, an outlier can be removed if it's a clear error, replaced with a more reasonable value, or retained if it's a legitimate part of the phenomenon being studied. Step 3 is correcting textual and numerical errors. Inconsistencies in text fields and simple typos can compromise data integrity. This involves standardizing text entries, for example, converting US, USA, and the United States to a single, consistent format and correcting obvious numerical typos. Step 4. Handling duplicate data. Duplicate records can artificially inflate the importance of certain values and skew statistical results. You need to identify and remove records that are either fully or partially duplicated, ensuring each data point is unique. Step 5 is standardizing units. For measurements to be comparable, they must be in the same unit. Make sure to convert all measurements to a uniform standard before analysis. For example, ensure all weights are in kilograms and all lengths are in meters. Step 6. Converting data types. Data is often stored in an incorrect format, like numbers as text, which prevents proper mathematical analysis. Ensure all columns are in the correct data type format, such as converting a column of numbers stored as text to a numeric type. And finally, step 7 is detecting inconsistencies. Some data may be syntactically correct but logically impossible. Apply logic rules to find and correct contradictory or unrealistic data points, such as an assay value for an oxide element reported as 110% or a negative concentration value. Once the dataset has been rigorously cleaned, we can proceed to the initial phase of analysis, understanding the fundamental characteristics of our variables through univariate analysis. Univariate analysis is the first and most fundamental step in EDA. It focuses on describing the characteristics of single variables, one at a time, without considering relationships between them. The primary purpose is to summarize the data through key statistics, understand its central tendency, or the typical value, and its dispersion, the spread of values. Measures of central tendency provide a single value that attempts to describe the center of a dataset. The three primary measures are the mean, median, and mode. The mean is the sum of all values divided by the count of values. It provides a summary of the average concentration. However, it's highly sensitive to outliers. A single high-grade sample can dramatically inflate the mean, potentially misrepresenting the bulk of the deposit. The median is the middle value in a dataset that has been sorted in order. It represents the typical concentration and is robust against outliers. It's often a more reliable measure than the mean for skewed geochemical data, as it's not affected by rare, extreme values. Finally, the mode is the value that appears most frequently in a dataset. It identifies the most common value or rock type. In geochemistry, this can help identify the dominant background concentration or the most prevalent lithology. A dataset can have one, more than one, or even no mode. That concludes the first part of our guide. We've covered the importance of EDA, how to classify data, sampling strategies, and the critical steps of data cleaning and initial analysis. Join us in part 2, where we'll dive deeper into univariate analysis by exploring measures of dispersion and data visualization. Thanks for watching, and don't forget to like and subscribe for more content.